My name is Steve Ackerman. I'm a professor over in atmospheric and oceanic sciences here at the University of Wisconsin in Madison, as well as director of the Cooperative Institute for Meteorological Satellite Studies. And I get the honor of introducing Dr. Louis Uccellini today for today's presentation. Dr. Uccellini is the National Oceanic and Atmospheric Assistant Administrator for Weather Services and Director of the National Weather Service, or NWS. In this role, he is responsible for the day-to-day civil weather operations for the United States, its territories, adjacent waters, and ocean areas. Devoted to the idea of public service, Dr. Uccellini has accepted the daunting task of ensuring that our National Weather Service is second to none, and one that supports a weather-ready nation. As we saw from this morning's weather impacts all facets of our lives, from commuting, but also to agriculture, even to the spread of diseases, to the economy, and beyond. And the National Weather Service exists to keep us all informed and safe. The agency does so in ways that are very public, such as issuing life-saving watches and warnings, and in less visible ways, such as supporting aviation and transportation safety. But despite the many advances in our nation's ability to forecast weather with precision and accuracy, injuries and death as a result of severe weather remain an unsettling fact. For our nation to become a truly weather-ready nation requires more than accurate forecasts. It includes communicating well with forecasters, decision-making, and the public. Under the leadership of Dr. Uccellini and working in partnership with other agencies, including research teams here at the University of Wisconsin in Madison, the National Weather Service's goal is to help prepare communities and local officials for the impacts of weather hazards in order to save lives and protect property. An alumnus of the University of Wisconsin-Madison, Louis is an unabashed Badger with long-standing connections, pride, and great affection for his alma mater. Louis received his Bachelor of Science, his master's, and PhD degrees from the University of Wisconsin in Madison, and he has published more than 60 journal articles and chapters and books, and is known for co-authoring the widely acclaimed 2-volume book, Northeast Snowstorms. And I point that out because personally, I want to see the 3-volume book on Midwest snowstorms someday.
You're going to have to write it.
Maybe John can. So with that, each of us, I want to point out, has a role to play in discussing how to actively prepare for being a weather-ready nation. So please join me in welcoming Louis as we address the question of how we as a nation can better prepare for extreme weather events and the impacts of weather on society. Louis?
Thank you. So that's yours. Am I on? Yeah, am I on? Yeah, great. Well, thank you, Steve. I appreciate that introduction. And yes, I grew up in New York, and I know I haven't lost the accent. I'm reminded of that all the time. But from an intellectual point of view, I grew up here. And it's still a tremendous university and a tremendous department. And I'm always delighted to come back. Before I give my talk, there were 3 people I wanted to introduce to the audience, people who in many ways impacted my life here at the University of Wisconsin. Stefan Hastenrath, who is a professor emeritus, who I TA'd for, and I knew I was making it when I actually met his standards. He set very high standards. John Young, if you could raise your hand. John was the youngest professor, the newest professor when I arrived. So when he sent out the notice that he was officially retiring, I really looked at that email for about 5 minutes and said, I can't believe it. John was on my master's committee and my PhD committee, and I gained tremendous insights from him in doing my work. And of course, Don Johnson, who is sitting up front here, Professor Emeritus, was my major PhD professor. And we're honoring Don with a special colloquium at the American Meteorological Society this February. And one of the reasons I'm here is doing the oral history project. And Don, so I'm there just to sort of channel the discussion where I can, but it's really been a pleasure just sitting through the last 2 days, and we got one more session to go. So Please give a round of applause for the three Professor Emeritus here. So the Weather Ready Nation is an important strategic goal for all of NOAA. In fact, we were just reviewed by the National Academy of Public Administration, NAPA, and they roundly embraced that as a strategic goal, and then said we can't do it alone, that other agencies, whether they're state, federal, local, have to be part of this process. And it really comes down to the individual, because now with cell phones, you'll be making your own decisions based on what you get on cell phones. And those decisions could mean the matter of life and death for you. So as we found out in the Oklahoma tornadoes, for example. So this Weather Ready Nation is really all about us. But when it comes down to us as meteorologists, what we really have to do is continue our advancing the prediction of extreme weather events, and I will emphasize that and then lead into the Weather Ready Nation at the end. So in the outline, I want to start off with 3 slides. This is based on Nate Silver's article in the Sunday Times about a year ago. The weatherman is not a moron. Now, there are times when my family doesn't believe that, but we'll see. All right. Why do predictions matter? What was this country like when we didn't have weather predictions and people were settling here? Got a few examples of that. Advancing the predictions of extreme events. And what's ironic here is that we're actually making better advancements on extreme events than perhaps we are on light to moderate events. And last night might be an illustration of that. And then taking the predictions beyond the weather forecast, and this is our outreach to decision makers. So we'll have a few slides on that, and advancing towards this Weather Ready Nation. So this was the Weatherman is Not a Moron was an article published by Nate Silver. Now, Nate Silver is the chap who predicted the elections last year, got every state right. And of course the national election from that. He actually did he's done a book on prediction, and basically what he said in this article, emphasized more in this article than in this book, that the weather forecasting stands out as the premier example in success in prediction. He actually visited the new building, the new NSEP building at the University of Maryland Research Park. This is a building I had a lot to do with, the 14-year project. I walked in this building and saw the atrium and the open areas. This is, the new architectural design. And this was his quote about it. And what he was trying to emphasize is the people who are making the forecast now and the high-tech aspect of it and the connections to decision-making reminded him of his walk through the Goldman Sachs trading floor, and he also noted when he talked about economic predictions that they're probably the worst. So that was that. But this is basically what came out of the article. That weather prediction has progressed when most other predictions have failed. Progress can be measured. This was very important to him. He's a very astute statistician, mathematician type, and it verified in a quantitative way. We include uncertainty. So this whole effort to include uncertainty is really important for decision making, especially since we can guarantee we can't make a perfect forecast. How good is good enough for decision makers to actually move forward is a very important part. And then he actually goes as far as stating the Weather Service does the best job in making these predictions and conveying the uncertainty in those parts. So this is the overview of the forecast process, and I have to be reminded at the, top one. All forecasts start with observations. As we'll see, they're becoming increasingly relying on remote sensing and satellite observations, and that was pioneered here at this school. You have to process these observations, derive all the useful information from them, done on these supercomputers. This is a data assimilation step, and then numerical modeling provides the central guidance. We provide these to the local forecast offices, who, this is where you get your forecast. your official Weather Service forecast, in this case from the Sullivan office. They are distributed, and they're now, we distribute this information to decision makers, to private sector, to media. We depend on the response and feedback, which influences every aspect of this forecast process. We have 122 local forecast offices around the country, including Puerto Rico, Hawaii, Guam, Alaska. We have 9 central NCEP centers. I was the director of NCEP for 14 years, and 5 of them at Maryland in that new building with climate, hydrometeorological prediction, which has just recently been changed to the Weather Prediction Center, Ocean Prediction, the Hurricane Center, Storm Prediction Center, Aviation, and the most recent center that joined the team here is the Space Weather Prediction Center, which is in Boulder, Colorado. Coronal mass ejections are producing these magnetic disturbances, which have tremendous influence on things like GPS, communication, aircraft operations. So we covered everything from the sun to the sea with these centers. So why do predictions matter? You see here, this is a book that was written by David Laskin, the children's blizzard. This is a blizzard that happened in 1888. I did it again. Of course, it was not forecast. In this era, the telegraph lines were just being strung along the railroad, developing railroad lines, and they were immediately being used by the Signal Corps to collect data and provide indications. They were not allowed to use the word forecast. They provided indications, and this started in October of 1887, less than a year before this blizzard. By the time the indications were released to the folks in the Dakotas, it was already too late. The kids left for school, people went about their business. These blizzards came on awfully fast. In this case, over 235 people perished. Another classic example, this is Isaac Storms. This is one of the best written books, by the way, on a particular, in my opinion. Again, there were poor analysis conditions for the Caribbean, the tropics in general, over oceans. There were indications that there were a storm out there south of Cuba, but they really didn't know where it was located, and they certainly didn't know whether it was going north or west. They lost it in the Gulf of Mexico. There was great initiative on the part of Isaac Klein in Galveston, Texas, to track the storm through the Gulf. In those days, the warnings were issued in Washington, D.C. There was no warning issued. There were muddled indications, communications about indications provided by the local forecasters. But folks were essentially on the beach, living right along the coast when this storm hit. At least 6,000 people died. There's no totally accurate count of how many people died. But at least 6,000 died in the Texas area alone. Now, so we're living in a world of, actually, we live in a country that has the most extreme weather than any country in the world. And the greatest varies, so we have hurricanes, tornadoes, we have these severe thunderstorms, droughts, and now increasingly these large wildfires and becoming very dangerous as population increases in areas prone to wildfires. The floods, either flash floods or the river stem floods. On average, there were about 650 deaths and about $15 billion in losses. But a trend line here is pretty disturbing when we add up those events that involve $15 billion and then to $25 billion in losses. You can see this increase. These are geophysical in red, the meteorological, hydrological flood, and then more climatological, especially the drought and now the wildfire, which really flares up in the dry conditions, obviously. And you see this almost exponential increase as we have these large number of events, and we've we see here, become more vulnerable to these events with an increasing number of people in the world. Obviously, in the United States, we've had an increase in population, especially along the coast. So where people are living, where we're building our infrastructure is more vulnerable to these events. Of course, we have to feed this increasing number of people, so we're vulnerability there. Energy, lighting up the infrastructure, this whole infrastructure has become more vulnerable. So we need to be able to predict, mitigate the impact of these events. So advancing the predictions. Clearly, in this era, actually from the 1880s through the 1940s, forecasts were essentially based on surface observations and taken every 8 hours and then 6 hours increment. Forecasting was very subjective. Analog techniques were used. The dependency upon forecaster experience is what drove the entire forecast process. It was considered an art at best. And in fact, among the science community, meteorology was mocked and by some not considered a science because it included forecasting as a fundamental part of its work, including Alfred Nobel, who would not consider meteorology as a category for the Nobel Prize. And we saw that with Lorentz, who, with the chaos theory, they would not give him the Nobel Prize because he did it as a meteorologist and not as a mathematician. Okay, so we have this transformation that occurred basically after World War II. We introduced numerical modeling, obviously by today's standards, very crude models in the 50s and 60s. Very slow progress. By the time we got into the 1970s, the limits of predictability were considered 12 to 24-hour lead time for many of these life-threatening events. Hurricane force winds and heavy snow had predictability measured in terms of hours out to 12 hours. The amount of snow above 4 inches was never predicted. The sign for a snowstorm for me growing up as a kid on Long Island was 4 inches or more. Okay, that's the best you could get in a forecast. We all look at numerical modeling today as an obvious centerpiece for the way we do our business, but it wasn't easy. Even in 1976, there were people scientists who wrote, in this case in the Bulletin of the American Meteorological Society, C.S. Ramesh, was advising us to abandon research that uses weather sequences generated in a computer as a basis for deduction about the real atmosphere. If you take out the word weather and put in climate here, you're hearing the same naysaying going on with respect to numerical simulation for the larger scale, longer time frame today, all right? So this was what we were up against when models were introduced in the Weather Service. There were folks in the Weather Service that termed it a cancer in the field of meteorology. So this was not a walk in the park for the numerical modelers to get this used. The 1970s, 80s, and 90s is when I think the foundation for the modern weather forecasting was laid down. The operational improvements for accessing data in real time, getting them into the computers, running the models, and getting them out in real time with enough resolution that they actually started capturing the big events. That started happening in the mid-1980s into the early 1990s. And that's when the transition occurred. So it took about 30 to 40 years of scientific effort around the world to get the numerical models to the point where they actually made a big difference in forecasting. So today, basically everything you read, see, or hear about weather, climate, and ocean forecast is based on numerical prediction models. And there are three fundamental components to this starting point. The global observing system, computers, the supercomputers and workstations, and meteorology and code breaking is what drove the requirements for the development of supercomputers. And Seymour Cray visited NCEP, and at the time it was NMC, and NSA quite regularly to develop his supercomputer, the Cray computing. And then data assimilation modeling science. So if you have a weakness in any one of these components, this will work against your abilities to actually predict these events. So today, in our observations, we ingest about 2 billion observations per day. And 99% of that is remotely sensed, mostly from satellites. And again, this department here in Space Science and Engineering Center rightly deserve a lot of credit for this. Vern Sumi was the father of the satellite meteorology, and this was his dream. And we certainly have realized his dream. The models themselves have now become Earth system models. When I did my work here, got my PhD, you could focus on one component or the other. We now have to deal with the coupling of the atmosphere, the ocean, the atmosphere and land, and the atmosphere and cryosphere to advance our prediction. Our global resolution is currently 27 kilometers. As we'll see with Sandy, this worked against us. Our North American resolution is down to 4 kilometers. So we're now running 4-kilometer models to predict the weather across the North American continent. The computer, we were running at 73 trillion calculations per second. That's, we had this computer filled, and it was not of the right capacity for all our requirements. We have recently, July 28th, stepped up to 208 trillion calculations per second on a new IBM Dataplex. As we'll fill this up rather quickly too. These are huge numbers. When I left Wisconsin and went to Goddard Space Flight Center, the big deal was to have a computer at 1 million calculations per second. So you get the idea that this is pretty fast computational speed. So let's see what we're doing with extreme events today. Briefly go over the Snowmageddon, the Midwest, Chicago. This is a February 2010 snowfall. I can tell you, you don't want to miss this forecast in Washington, D.C. You just don't want to do that, and we didn't. The Midwest Chicago blizzard, a really tough forecast with this blizzard predicted 4 days in advance. The Alabama tornado outbreak, the good news here is the forecast. The bad news is the number of deaths, and this will get us into the Weather Ready Nation conversation we're going to have here. And then Sandy, which was obviously a major storm system for the eastern half of the country, as it turns out. Okay, so this is the radar depiction for the snowstorm that buried, the first of 2 snowfalls that buried Washington, D.C. with close to 4 feet of snow, and the second one was coming across on the tail end of this. What's interesting here, the white, that's the watches, and then the red's the warnings. And we had these out well in advance. This storm was predicted 7 days in advance and very consistently leading right up. And what's important here is not only where we predicted the heavy snow, but notice the cutoff right through New York City. So we did not predict for New England. So we didn't over-predict it, and that's really important. So there's about 25 million people in this area. We did not have to get overly alarmed. They did not have to get overly alarmed about this. Tremendous storm system. It paralyzed the Mid-Atlantic coast. You see up over 3 feet of snow over a large area, and then followed by 1 to 2 feet of snow with about 40 to 50 mile-an-hour winds. So it completely crippled the Mid-Atlantic region. The storm system was predicted 7 days in advance, the potential for heavy snow 3 to 5 days in advance. The forecast actually called for feet of snow 3 days in advance. So the state implemented COOP plans, shelter-in-place plans, 2 days before the event. And I have to tell you that when that happens and you're there as a forecaster or you're in charge of the forecasting group, you're just saying, we better be right. I mean, you're telling people that they are basically going to be stuck in their houses for 3, 4, 5 days. Airlines cancel flight in advance. This allows them to spin back up faster. You don't want your plane buried in 4 to 5 feet of snow. Let them clear the airport and then get back in. The retail industry were pre-stocking shelves, having pre-storm sales across the board, not just snow shovels. We're talking every retail sale, because they were supposed to have these big sales on the weekend. This first storm occurred on a weekend, so they had their sale on Wednesday, Thursday, Friday before, well before the first flakes of snow. Then we get the Chicago blizzard. What's interesting here is There's nothing here. Look, there's nothing upstream. You got all these watches and warnings going out. And here it comes. And it blows up and maps right in, and then you get the second area up here in New England. I could tell you, I was talking to Tom Skilling about this, a WGN meteorologist in Chicago, and he spent a day trying to ward off his producer and other naysayers, saying, there's nothing going to happen. Look, there's nothing there. You're just overhyping the storm. This is what the forecasters have to deal with when you're trying to give an advance forecast and outlook for these kind of storms that aren't there, that develop upstream of you, and you're forecasting them 4 or 5 days in advance. So this was really a remarkable forecast. Blizzard conditions, 10+ inches of snow across a large portion of the Midwest. Chicago buried by wind-driven 20-inch snowfall. The public schools were closed for the first time in 12 years. The blizzard itself was predicted 4 days in advance. Now, we trace this back to the previous century. No warning, no forecast to 4 days in advance. You did not want to be caught in this storm. Flights canceled. They declared emergency and ordered the National Guard well before the storm actually formed. Now, another interesting thing about this storm, on the left, here's your surface analysis, 18Z this is 1 o'clock in the afternoon here, 0Z, and then 6Z. So this are 6-hour increments, your surface analysis. And you see the actual radar with these bands that form, very heavy bands. This is the simulated radar from our 4-kilometer model runs. And this is what the models were saying these radars would look like. And if you put this in motion, you can see it developed the storm and it just moved it up. Very, very tight northern boundary. That's a real forecasting nightmare. It's not, again, not only where is it going to snow, but where is it not going to snow. And you see how it was forecasting these areas of very heavy snow. And then it's how it shoots over to New England. Okay, so it's not just a matter of moving this across. This snow area that affected New England really developed very rapidly up there in that part of the storm. So the models have really come a long way. Those are the snow events. This is the Alabama, April 27, 28, 2011. 190 tornadoes, 311 fatalities. The deadliest outbreak since 1932. The outlook was issued by the Storm Prediction Center, one of those national centers I noted earlier. 5 days prior, the moderate risk issued 3 days. High risk issued 16 hours in advance. The coordination calls and co-location with FEMA actually occurred 3 days in advance, and this initiates a whole downscaling of interactions with state emergency and then local emergency managers. The probability of detection was 96% for the tornadoes occurring within the watches, and the average warning lead time was 24 minutes. And you can see when you see this radar, people were ready for this event. The general public was ready, and you can see how massive this outbreak is and how dangerous these storms are. And yet we still lost 311 people just from this outbreak. And this was before the Joplin, Missouri, where we lost over 100 people as well. So we'll get back to that at the end. And then there's Sandy. This is the high res. We were comparing notes about the Folk Show Wisconsin. This is 1 minute imagery, right? This is the one special from the GOES 14. And this was an amazing storm system. First of all, look how big it is. Fills in this whole basin area and then extends all the way back into the Great Lakes. And then notice as this thing starts moving in, it starts accelerating. Oh, we don't get to that point. Wrong image. This storm from this point on not only moved towards New Jersey, but was accelerating, which makes it even more dangerous. The nature of this storm, there were 4 principal impacts of Hurricane Sandy. First of all, the peak wind gust exceeding hurricane force winds and tropical storm force winds covered a very large area, a very populated area, affecting over 50 million people just from this alone. Here's your track coming in. The total precipitation, very heavy rains, over 10 inches of rain in the Delmarva Peninsula, 6 to 10 inches in the Mid-Atlantic region. The reason we didn't have major flooding with this case is we didn't have the rains before the event. It was a rather dry ground, so we lucked out in that regard. West Virginia and North Carolina, unfortunately, did not luck out. Over 3 feet of snow, very cold air came pouring into this system. It was a hybrid storm, extratropical and tropical. This is the first time in the history of the National Hurricane Center where blizzard warnings were issued as part of a landfalling storm system. 3 feet predicted 3 days in advance, as I'll show you. And that size I was telling you about, the storm surge, we had very significant storm surge in New Jersey, Long Island Sound, up along the New England coast, and the Great Lakes, including records set in Lake Michigan and Lake Huron. So you get a sense of the massive nature of this storm. Developed, the hurricane actually, and we'll see this in the satellites in a minute, and then moved up the coast. This October 27th, October 28th, 29th, it actually made a jog to the right and then came slamming into New Jersey. This track, bringing it back from east to west, is particularly dangerous. Most people were hoping that it would just go out to sea, but notice how this high pressure system is building up over the top. And aloft, you had a similar type of situation that was driving it to the west. And then, you, as we'll see later, the fetch of water from the Mid-Atlantic all the way into northern New Jersey and New York Harbor. This was the worst case scenario. You don't want to be north of a system like this that's moving from east to west. Aloft, for the meteorologist in the room, we have this omega block that was forming as Sandy was forming as a hurricane down here. And the big forecast issue was, how deep would this trough be? How strong would this ridge be? So one track of forecast would have this turning out to sea, not captured by this trough and underrunning the ridge, and others had it captured by this trough and ridge and driven back in. And the model that did that most successfully was the European Center model. So here's the satellite for Sandy, as it developed as a hurricane, it actually got to a Category 2. And here's the 5-day forecast. The forecasters were looking at all the models and actually forecast 5 days in advance this turn to New Jersey. We've gone back and looked over at least 200 years of data based on the ship reports, especially in the olden days. We don't think there's another storm that's actually done this. So to actually forecast it 5 days in advance is quite remarkable. I mentioned the rainfall, the very heavy rain. Here's the verification, up over close to a foot of rain in the Delmarva. Here's the 3-day forecast, accumulated forecast. It was HPC at the time, now the Weather Prediction Center. So it got pretty close to the amounts, and it certainly got this turn to the west. And notice the heavy amount of precipitation in West Virginia, and that's where the 3 feet of snow was actually predicted 3 days in advance. So for a landfalling, either hurricane or hybrid storm, at that time we didn't know when it would make the transition. We weren't quite sure. But to predict this amount of snow and get people ready, and when I was talking to Craig Fugate, the director of FEMA, they were particularly concerned about this because people's houses still had the tarp on the roofs. The houses, those roofs had not been repaired from the derecho, which had crossed this area in June. A lot of damage to houses and other buildings in this area made this particularly a hard-hit region. So he was actually marshaling the FEMA response and the state response for West Virginia into North Carolina. He was focusing on this as much as he was focusing on the coastal areas. I mentioned the long fetch. It was a two-storm system. We had that omega block. So you have Sandy here, another storm system here, and you see this easterly flow from almost 2/3 of the way across the Atlantic. This is forcing your water right into the area north of the storm, and it all got focused on the Long Island Sound and the Raritan Bay and the New York Bay. We predicted up to 50-foot waves 36 hours prior to the storm, which we do have verification for. And of course, the surge itself This diagram here is a surge forecast that we presented to the New York City officials on the very early Sunday morning. The green here is your normal tides. The yellow is the surge, and notice we were predicting the surge right about at this high tide. The actual is the black. This is our forecast. And you see something here which always gets us concerned. If you get a rise through 2 or 3 tidal cycles, you know you've got, so the perfect storm was like this, okay? You got 2 or 3 tidal cycles, and you get your low tide, which is higher than the normal high tide. You know you got a problem. So we were predicting 11 feet for the Battery of New York. This is the southern tip of Manhattan Island. This was a record forecast. It actually verified at 14 feet, okay? So obviously, and if you were watching TV that night, they had gone through this period in the afternoon. There were merchants in the Battery telling folks we had dodged the bullet, come on down and eat here. And I'm in front of the TV going, no, no, no. And this was coming up. Jim Cantori was standing there at the Battery Park, and within 15 minutes, the water went from over his boots up to his waist. This was coming in full bore. Our communication strategy, we want people to take action. So Craig Fugate and I were on the call for the media for 2 straight days, and then Rick Knabb from the Hurricane Center was with us as well. We had to emphasize the unique nature of the storm, the large area, the east to west track toward New Jersey, the record surge and inundation in New Jersey, New York City, and southeast New England. This really had to be emphasized that this was not your normal storm moving up the coast like Irene the year before that didn't create as much damage as was expected. We emphasized the worst case scenario. We compared it to the perfect storm. We had to emphasize the record blizzard. How do you tell folks you're going to get 3 feet of snow from a tropical storm? So we had to convince people. Just to look at some of the models real quick. The observed track is this blue. We've all heard about the European Center turning this. This is what we call the explicit forecast, the single run. And you see it did turn it towards the west. This particular run actually had it a bit too far south. Our models, which by this time was showing some kind of a turn, but still had it too far out. The ensembles are what we're showing here. These are multiple runs of the same model, and we perturbed the initial state because there's a lot of uncertainty in the forecast. And the ensembles from these runs were showing a convergence not only towards where the actual track was, but the turn right to New Jersey. So it was really the ensembles that the forecasters were using when they took that storm and moved it from here and then turned it towards the west. The ensembles were also important for showing that acceleration. Now, you see here, these are like 20 different versions, and there's a nice, this is out through 24 to 36 hours. It starts spreading out, but there's still a maximum number of runs which are aiming it at New Jersey. The main thing we were emphasizing at this point was the acceleration of the storm, because that takes all of that water, not only drives it in, but with the accelerating storm, really concentrates it and brings it in very strongly. So we knew that northern New Jersey, and of course the governor knew, all the local governments here were already prepared that this was really, truly the worst case scenario for that part of the country. Okay, so we verify, the Hurricane Center verifies all the forecasts. These are 12, 24, 36, 48, 60, 72, day 3, day 4, day 5. And you see all the forecasts have an increase in error as you go out, except the European Center. And then we get hit by folks, in the community, why are our models so bad, et cetera, et cetera. So what we've done since then, we had this, we were blessed with the Sandy Supplemental. This came about right after I took over the Weather Service, and we worked, they made an amount of money available, but we had to come back with a spend plan. And one of the things I focused on was building up the operational computing capacity, because you can see we had half the computing capacity of the European Center, so they could run models at higher resolution. So now we're catching up to them with this recent increase up to 208 trillion calculations per second, but by next year they're already doubling us with their Power 7. But the Sandy Supplemental, by the end of fiscal year 15, will have us up to 1,900 trillion calculations per second. We're now in the petaflop range, and this is going to be hugely important. I'm convinced, I already know the European Center has seen this chart, and they're already planning to be up here fiscal year 16, so, you know, we're off to the races. But here's why it's important. Here's our operational model at 27 kilometers. We were telling folks, and this is true, it's not just for this model, but for our ensembles, for our high-res rapid refresh, we have a lot of these advances ready to be moved in, but we didn't have the computing capacity to handle it. Here's what happens when you take that same model and run it at 13 kilometers from the same initial state. It curves it back in. It got the deeper trough coming in, and it built that ridge over the top. This storm had no place to go but to the west to New Jersey. The high resolution deterministic and ensemble models provided the consistent alert 7 days in advance, yet it over-forecast the storm intensity. But the fact is, we got the initial alert for this being a danger to the East Coast, being a unique storm from that model system. Our models basically caught up in the day 4 time range. The forecasters relied on the model ensembles from all the centers, beginning Thursday and through the event the storm made landfall Monday night. We communicated with FEMA, emergency management community, the media, right down to the local level about the dangerous nature of this storm. This was hugely important for areas that weren't used to seeing something like this. Evacuations were initiated 3 days in advance with confidence. It's what they actually cleared out parts of Long Island that I know as a kid people never would have left. The forecast, I believe, saved lives. I have no doubt about that. So the ongoing research points to model resolution. We do need improved physics and improved data assimilation with that higher resolution. All right, so we want to take these forecasts beyond the weather, and this is what the Weather Ready Nation is all about. So we want to build community resilience in the face of increasing vulnerability to extreme weather. We want people to make decisions based on our forecast, when I say our, in this case, the whole enterprise, because the United States has this public-private partnership with the private weather sector that no other place in the world has. And I think that makes for the best forecast in this country. In that sense, as an enterprise, we're already second to none. So NOAA is developing new decision support services. We're improving technology, outreach. We're expanding our dissemination ability to get the data out in ways that people can understand. One of the things I learned from being the AMS president and developing the presidential forum with Microsoft and Google, these folks are emphasizing that with cell phones, you will all be the decision makers. We have to get this information to the cell phones because as we're seeing, like in Fukushima and other worldwide disasters, people are using the cell phones to download the information for them to make decisions. They're not waiting for somebody to tell them what to do. So this is a huge challenge for us, but it's also hugely important. For me, my personal aha moment was the April 27, 28, 2011 tornado outbreak. We were all proud of our forecasts and outlooks, but the fact is the number of people died was a very sobering experience for everybody involved. We had this workshop in Norman, Oklahoma in December 2011. We had full engagement of decision makers at every level. Social scientists were fully engaged in this conversation. And what we learned is what we think, they're even challenging us in terms of what we mean as a warning. Because people will receive our messages and process them differently than what we think they are processing them. And then you have challenges like, if we do a 30-minute warning with complete confidence, if the mother and father are here and the children are here, they're going to drive to where their kids are. And the worst place they can be is in a car. But if you give them increasing lead time with confidence, they're going to get in that car and they're going to cross town to be with their kids. All right, we're learning this. And this, they want second and third sources of information. So this is becoming a very important aspect of what we're doing. It's not just how good we are as scientists, it's how do we assess and update our warning and our dissemination strategy? How do we integrate the social and physical sciences? And I've just said this, and this is leading us to get to these impact-based forecasts and warnings, conveying the level of danger that's involved with these storms. Big difference between a Cat 3, 4, 5 tornado and a 0, 1, 2. So we have to start conveying that. We have to reduce our false alarm rate so people have confidence in what we're doing. So this is improved outreach and education. We have one WCM, Rusty Capella is in the audience here. We're going to have a WCM conference this year. We're going to have it in Norman, Oklahoma. It's the cheapest venue we could get, but it also turns out that that's where the Severe Weather Center is. And we're going to have this social and physical science connection brought to them because they're the folks doing the outreach and with the emergency management community and education throughout the United States, and we have to start bringing this message down. So we want to provide superior decision support, foundational information and services. We want to invest in the science and technology to ensure that we can develop the best forecast, we can message that forecast, and we can get it out. And we want to empower our workforce. We are now embedding our workforce in places like Center for Disease Control, in emergency operations centers. They have to understand how these decisions are made, and then they're the tip of the spear for all the information that's brought from this forecast for these folks to make the decisions that they have to make to save lives. One last thing, I mentioned the Earth system prediction. We are now, remember I emphasized how meteorology was mocked because it had forecasts as a fundamental part of its science. Hydrology has ecology now is looking at prediction. This has happened over the last 10 years. You can actually connect the weather forecast, the hydrology forecast, and the ecology forecast. If we can predict the rainfall, which we do, and the runoff of that rainfall, we do, if we have the nutrient loading, you can actually predict the ecology of the bay, the river, the coast, and where that water is going. And you can do things like a health forecast, a beach forecast, a water quality forecast. And there are research units that are beginning to do that. This is a group that's involved with the Great Lakes Environmental Research Lab, one of the laboratories in OAR and NOAA. And these are beach forecasts that are being made in an experimental mode. We're also doing this in some of the bays in the East Coast. And people are taking notice. You really don't want to go swimming. If you know 2 days in advance that you have the possibility of these things happening, you don't want to find out 2 days after you've gone swimming, like my youngest son just found out, okay? Because this is pretty nasty stuff, all right? And this is doable. This is now doable. And people are actually, in these various sciences, including the health sciences, are taking prediction very seriously. Everybody will tell you, get ahead of the curve. So, in summary, we're making historic strides in predicting extreme events 4 to 8 days in advance. When I was a student here at the University of Wisconsin, we all agreed if we could get a forecast in our career out to 36 hours, it would be, we'd claim success. No one believed we could do this out to 4 to 8 days in advance. Linking these forecasts with decision makers to mitigate impact, save lives in the face of extreme events is our top priority. It is the basis for the weather-ready nation. Expanding prediction into other scientific disciplines. I had a lot of fun with the ecology folks. I got thrown out of their first 2 meetings about 10 years ago. We only do assessments. Assessments take 10 years. We'll see you a decade from now. So now they see me every day. And it will have a profound impact on our lives, all right? Because we're really talking about the health here. And we're doing this globally, by the way. We're doing this in Africa for cholera and malaria. We actually do forecasts through our African desk for cholera and malaria. And it's really profound what's going on there. So we're on the forefront, the National Weather Service is on the forefront of these historic movements toward a weather-ready nation, making the nation resilient to extreme weather. So I thank you for your help in us building this weather-ready nation. And